Now, for question 3, it's a 5-part question, but they're mostly easy, and we're going to use something from pre-calc, actually. As you can see right here, we have an equation that describes the displacement of a spring attached with an object, attached with a ball. And let me go ahead and draw this picture first. So, so that's the wall, that is the ground. And we have a spring, and the spring is attached with the ball. And let's just say this is the equilibrium position. So the first question is, hey, what's the amplitude of this? What's the amplitude of this ball's motion? So I would say, if you remember how to read your sinusoidal function, 0.35 cosine 15t. 0.35 meters is correct. Okay, so that's 0.350 meters. Okay, so the object's gonna bounce back and forth, and it's gonna be oscillating between a 0.35 and negative 0.35. Okay, now it also gives you the spring constant right here. We probably would use it in a moment. Now, since we're talking about pre-calc, okay, do you remember how we have a few features, you know, to tell? And the first one was the amplitude, the A value right there. The number in front of t, which we call the B value. What do we use the B for? What do we tell using the B value? The 15. Yeah. Which we call it what? Well, it's a horizontal stretch and shrink, but we have a very specific term for it. You know, sine and cosine would be for one thing by default, and then a tangent, cotangent, it has another value for it. Period.
Oh, wait. Sorry.
Period.
B equals period. Yeah.
How do you calculate period?
B divided by 2 pi. 2 pi divided by B.
Okay. Because when B is 1, which you don't see it, it's 2 pi. Sine and cosine are both 2 pi by default. So what's the period in this case? Two pi over 15. So the 2 pi over 15 seconds, it's your exact answer for your period. So what I want to show you here is that not only can you use the formula to calculate period, you may also use your pre-calc knowledge to tell the period. So do not be surprised that you are given an equation like this, and then you have to get the period from the equation itself. And let's go to part B. Huh? Well, they're gonna just learn it by knowing how B affects the graph. Okay, so what's the frequency? We got the period. So frequency is simply or you just flip the fraction. 15 over 2 pi hertz. Of course, we need to use a calculator for this, and make sure that you put a pair of parentheses around the 2 theta, or else you are going to confuse, or you are going to miscommunicate with the calculator. So that's going to be 2.39 hertz. Okay. So so instead of just going to part B, I actually prepared you to answer part B. So far, so good. All right. So pretty easy. Now we got the period. We know the spring constant. Can you calculate the mass on the next page? Since we know the way to find the period of a spring, right? With this particular equation. So can you go ahead and find out the mass, because you know everything. The question gives you the spring constant. You just found out the period. Mass is the only unknown. So could you go ahead and find it out? So the period, it's 2 pi over 15. So we kept 2 pi on the other side as well. So we can simply cross those out. Again, the spring constant is given to us by the question. So we simply square both sides. So after we square both sides, we have 1 over 225 times 200. That's basically your M. So 200 divided by 225, it's 0.889 or 0.89 kilograms. Now be aware that all the units, okay, in mass must be in kilograms. All the length units must be in meters. Okay, if you ever see any question that does not give you these two units, then you've got to adjust it and change it. All right, this might be the first hard question out of the 5-part question. So what's the total mechanical energy? Okay, let me bring back the picture that I drew earlier. What kind of mechanical energy it's available here? We got spring potential, right? Where would it have the highest spring potential energy? Compressed? And stretched. Yeah, when it's compressed or stretched, that would be the elastic potential energy right there. So right in the middle, it's not compressed at all. So I would assume that it has no spring potential energy or elastic potential energy. What kind of energy would it have in the middle? Kinetic. That's why it's moving. And by the way, we also like to label the same thing that I asked you earlier in terms of velocity and acceleration. It's going to be the same thing. That at the end of it, the velocity is 0. In the middle of it, this is where it has the maximum velocity. And then for acceleration, we have the maximum acceleration on the end of it. Okay, and since we have a spring, we have spring constant. Hey, we have everything that we need to calculate our spring potential energy. Our elastic potential energy, which is 1/2 K delta X square. You got the 200 for the K, and you have the 0.35 as your 0.35 as your compressed distance. 0.35 meters square. So 0.35 square times 100. It's 12.25 joules. So the closest one. Okay, so it's not really that bad, and that's why I said the stuff right here that we're doing right now, it still belongs to the umbrella of conservation of energy. And now, just the final part of this question. What is the ball's maximum speed? And we set right in the middle, right? It has the maximum kinetic energy because there's no more elastic potential energy. So how do we find out the velocity of the ball? Equals to 1/2 mv squared is equal to what? Yeah, that's the energy that that it had, right? And at the end of it, and when it's in the middle, all the elastic potential energy is converted to kinetic energy. And we are going to use the mass that we calculated earlier for this particular question. So what's the velocity here? We will square it at the end, yes, because we are finding v, not v squared. So after you multiply by 2, divided by 0.89, you will go ahead and square root that. And that is going to be 5.25. Now, if you have a hard time finding the square root button, do you know you can raise it to a power? What power is equivalent to square root? Yeah, so just raise it to 0.5 power. That's what I've been doing because I'm lazy finding out or typing the square root. And that's actually a good thing to get you ready for calculus. Because in calculus, we do a lot of exponents. Yeah. Like a lot of exponents. Yeah. I tell people, in calculus, exponents is like a daily diet. You deal with exponents on a daily basis. You use some of it in pre-calc, but the what? The values of it? Yes, you do. Yes. My table will work sufficiently. Well, the whole method, not just the table. Like how do you, yeah. I mean, same thing, either way.